Welcome to the Marine Electrotechnology channel. In this video, we will explain the working principles of the brushless exciter. We will discuss some important expressions and components in the exciter. We will start by explaining the main parts of the circuit, then the operation, then some of the practical faults which happen on board ships. We will discuss also why we should have AVR on any generator, and we will explain what the meaning of generator voltage drop. We will explain also the factors affecting the output voltage of the generator, and also the factors on which the frequency depends on. Also, we will explain the SSR, which is the surge suppression resistor, operation, and the possible faults, spikes and surges, motoring of a generator, and the protection and the protective devices provided for this fault. Also, in the rectifier, we will discuss the two possible faults of the diodes, and finally we will discuss why we should supply the rotor with a DC current, not AC. The main important equation here is the Faraday's law, and it explains how a voltage is produced in a coil whenever we have a variable magnetic field. This is the variable magnetic field, d phi over dt, or rate of change of flux with respect to time. Whenever a variable magnetic field intersecting a coil with n turns, okay, we will have a voltage produced between the two ends of the coil, and this voltage is opposite to the voltage producing the current, or the original current, which produces the flux. Okay, so whenever we have a variable magnetic field intersecting a coil with any number of turns, a voltage will be produced on that coil. If d phi over dt equals 0, or the magnetic flux is not variable, it is a constant flux, d phi over dt, it will be 0, and E also, it will be what? It will be 0. It means that no voltage will be produced on that coil. We have many other applications, not only the generators, many other applications working on this principle, like antennas and transformers and motors. The main parts of the brushless exciter are the AVR and the exciter stator and the exciter rotor. Here is the rectifier, three-phase rectifier, because these coils are three-phase also. And here we have the surge suppression resistor and the rotor. The rotor will be supplied by a DC current to produce the magnetic field. This magnetic field will be intersecting with the stator to produce the required voltage. This voltage, if the main circuit breaker is closed, will be applied to the main bus bars. Then after that, it will be applied to distribution panels or distribution boards and the molded case circuit breakers. After that, the power will be going to the loads. Of course, we have here the prime mover, which will be giving the mechanical energy to rotate the exciter. When we have a DC current supplied to the rotor, we will have a constant, non-variable magnetic field, and because of the motion of the prime mover, which is mostly a diesel engine, this magnetic field will be as a variable magnetic field intersecting the stator coils. After that, according to Faraday's law, a voltage will be produced on each coil of the stator. And the output voltage is applied here to the AVR. The AVR is adjusted for the required voltage in order to keep the output voltage of the generator at the set value or the required voltage. Now, why we should have an AVR, automatic voltage regulator circuit? For example, suppose that you applied 220 volts on a two wires for a long distance to a load. Yeah, here is a load. From here, you apply 220 volts, and how much do you think the voltage will reach the load? And this distance between the applied voltage and the load, say it is 1 kilometer. Okay, of course, the cables here, it will have a certain resistance. Okay, suppose that this resistance is 1 ohm, and the load's current here, for example, is 10 amps. Okay, so 10 amperes will be passing in the cables. Okay, the voltage drop will be accumulating on the resistance of about 10 multiplied by 1, which is 10 volts. So V here will be about 210 volts. Okay, the same here in the generator. Okay, suppose that we don't have an AVR and we have here an exciter current supplying the rotor. If we don't have an AVR, it means this current will all the time be constant. So the flux produced from the coil, from the rotor coil also, it will be constant. Okay, intersecting this flux with the stator, you will have an E. Okay, now this is the produced voltage inside the coils of the generator, but it is not the output voltage of the generator. The output voltage here is V. And what's the relation between V and E? You can compare this question by the example which we explained before. E is the transmitted voltage and V is the voltage which will reach to the load. Okay, and the difference between these two voltages is the voltage drop in the cables, or here in the generator is the voltage drop in the generator or stator coils. Okay, so if you want to calculate V, it will be equal to the produced voltage minus the voltage drop in the coils, which it depends on the impedance, or the impedance, which is the reactive inductance of the coil plus the resistance. So now, if the circuit breaker, the main circuit breaker is open, okay, there is I, it will be 0, so there will be no voltage drop in the coils. Okay, but once you close the circuit breaker and the current is passing to the loads, okay, you will have a voltage drop in the coils, and this voltage drop equals to I multiplied by Z, and this value, it will be subtracted from the produced voltage in the coils, and V, which is the output voltage, will be equal to E minus the voltage drop inside the coils. So when I is increased, V, it will reduce, okay, for a constant value of DC. Now, if you operate another loads, I will increase more, and V will decrease also more, okay, until it will reach something like this, as a relation between the voltage and the current taken by the generator. At zero current or with no load, the voltage will be equal to the required voltage, say it is 440. Okay, when the current is increased or when you operate more load, the voltage will be reduced like this. Okay, until at a certain time it will reach what? It will reach zero. The output voltage of the generator, it will reach zero. Okay, and at this point we will call this is I short circuit. When the current taken by the load is huge current, okay, the voltage will be reduced to zero. Because of that, we cannot operate any generator without an AVR. Now, what's the function of the AVR? Now, the produced voltage here is V. It will be applied to the input of the AVR. So the AVR will be comparing the input voltage or the output voltage of the generator to a set value, which is, for example, 440. And here it will produce, the AVR will produce an error signal, okay, according to the difference between the generator voltage and the set value in the AVR, okay. Now, if the AVR found that the voltage or the output voltage is reduced, okay, when you operate a load, it will increase what? Its output voltage. Once its output voltage is increased, the flux here will be also increased, and this flux will be intersecting with the stator coil while the prime mover is moving, so more voltage will be induced in the exciter rotor, and the DC voltage after the rectifier, it will also be increased. And if the output voltage of the rectifier is increased, it means IDC here will be increased, and the flux here in the rotor coil also will be increased. Now, intersecting this flux with the stator coils will increase what? The output voltage, and return it to the required value. Now, suppose that the output voltage is more than required. Say it is 460 volts. So at the input of the AVR, you will have 460 volt. So now it will compare, the AVR will compare this voltage with the set value, okay? And after that, an error signal will be produced. The AVR will reduce this error signal, so the flux in the stator coil will be reduced, and the voltage which will be produced in the exciter rotor also it will be reduced, and the voltage, the output voltage of the rectifier also, it will be reduced, okay, and the DC current also, it will be reduced, so the flux intensity in the rotor coil also it will be reduced. Intersecting this flux with the stator coil will produce what? A less voltage until it's returning back to 440 or the required voltage. If the output voltage here is 440, the AVR will keep the error signal constant in order to keep the output voltage of the generator at the required value. Of course, when you increase the load, the voltage drop of the generator will increase inside the coils, and the output voltage of the generator will be reduced. So the AVR, finally, it will increase the IDC current to return back the voltage to the set value. If the voltage is increased by reducing some loads, okay, so the output voltage of the generator will increase, so the AVR will reduce the error signal in order to reduce the output voltage of the generator to the set value. If the output voltage of the generator is the same as the required or as the set value in the AVR, it will keep what? The output voltage the same, and the output voltage of the generator will stay the same. Now, according to Faraday's law, E equals to minus N multiplied by d phi over dt. So whenever we have a variable flux d phi over dt intersecting a coil with N turns, a voltage will be produced between the terminals of that coil, okay? So the voltage produced, or the output voltage of the generator, by intersecting the flux coming from the rotor to be intersected by the stator coils, okay? So a voltage here, or E, it will be produced, and this E is proportional to number of turns of the stator coils and the magnitude of the flux coming from the rotor coil and the speed of rotation, which is d phi over dt. Whenever n is increased, E, it will be increased, and whenever phi is increased, also E will be increased, and whenever the speed of intersecting the flux with the stator coils is increased, also E will be increased. These are the factors on which the output voltage of the generator depends on, okay? Now, what's the frequency? If you have, for example, one pole, pair of poles, south and north, and you have a coil inside, okay? Now the flux is coming like this. Now if you want to see the voltage, for example, produced in this coil, it will be 0. In order to have a voltage, you should have a variable flux intersecting the coil. Without moving the coil or moving the or rotating the poles, okay, the voltage induced in the coil will be zero. So if we start to rotate the coil inside the flux, now it is at a zero angle, for example, okay. Suppose now at zero, okay, no flux will be intersecting the coil. Once you rotate the coil with an angle, for example, like this, 30 degrees, okay, some of the flux lines will be intersecting the coil and the voltage will be produced in the coil. If you increase the angle like this, more flux lines will be intersecting and more voltage will be produced in the coil, okay. The maximum flux value which will be intersecting the coil is at 90 degrees. So at 90 degrees here, you will have the maximum voltage produced in the coil. After that, between 90 and 180, okay, the number of flux lines intersecting the coil will be reduced, so the voltage also it will be reduced until it reach 180. Okay, the voltage will be again zero. Okay, between 180 and 270, it will start repeating the waveform, repeating itself again. It will increase, okay, but the voltage will be in the opposite direction, so it will increase like this to the maximum at 270. Then from 270 to 0 or to 360, it will be reduced like this until it reach the 0 again. Okay, so in one revolution for the coil, one waveform is produced like this. This is what we call it the AC waveform or signal. Okay, now if the speed of rotation of the coil is made to be 1 second, it means in 1 second I rotate the coil at 360 degrees, okay, or one revolution. What I will get from here, I will get one cycle like this. Okay, now if in 1 second I increase, so here what will be the frequency or the repetition of the signal? It will be 1 cycle per second, which is equal to 1 hertz, which is the unit of the frequency. Now if I increase the number of rotations in 1 second, it means if in 1 second I made 720 degrees or 2 rotations, what I will get? I will get 2 waveforms like this. 2 waveforms. So if I increase the rotation, I will get 2 waveforms. So the frequency of the generator now it will be 2 cycles per second, and that equals to what? To 2 hertz. 2 hertz. Okay. So as you can see, the frequency of the generator mainly depends on the speed of rotation. Okay. So if I made 50 rotations per 1 second, or 50 cycles per 1 second, I will get what? 50 hertz. This is if I have only, this will happen if I have only one pair of poles. But if I have another pair of poles like this here, okay, in every revolution I will get 2 cycles. Okay, so the frequency will be equal to the revolutions per second multiply by P, which is the number of pair of poles. Okay, if pair of poles, for example, is 1 and you made, for example, 50 revolutions in 1 second, you will have 50 hertz. If you increase the pair of poles and you make them 2 and you make 50 revolutions, you will get what? 100 hertz. So the frequency depends on 2 factors: the speed of rotation and the pair of poles. Okay, so if we have a reduced frequency, for example, in a generator which is supposed to give 50 hertz, it gives me, for example, 48 hertz. Okay, so it is not actually an electrical problem. You will go directly where? To the prime mover and check why the speed of the diesel engine is reduced. So we can summarize now that the voltage, the output voltage of the generator depends on the uh, number of turns and the speed of rotation and the uh, flux intensity coming from the rotor coil, and the frequency of the output depends on the speed and on the pair of poles, number of pair of poles. Okay. Now, when you operate certain loads, as we explained before, the voltage of the generator, it will be what? It will be reduced. Okay. Now, we designed these generators in order the AVR will increase the excitation, or finally the IDC, which is coming to the rotor, in order to raise up the output voltage of the generator to be equal to the required value. Okay. And we will not increase the speed. Okay, this is the question, why we are not increasing the speed, while increasing the speed also will raise up the voltage. The answer of this is because if you increase the speed, you will change the output frequency. So mostly we are keeping the speed constant and only increasing the IDC by the AVR and its output voltage to the exciter stator, then to the exciter rotor, and we can increase the voltage by this process using the AVR and keeping the speed constant in order not to affect the frequency of the generator. Now, whenever you have an increased load, what will be happening to the generator? First, the output voltage of the generator will be reduced, and also the speed of the generator also, it will be what? It will be reduced. Why the speed is reduced? Because the current which is taken by the load, and it will make a flux intensity from here, it will make a flux, and this flux is opposing the flux coming from the rotor. So when you increase the load, this opposition between the stator coil and the rotor coil is increased, so the speed of the finally the prime mover, it will be what? It will be reduced. What we will do when the speed is reduced, the frequency, it will be reduced. So we will have here a governor on the prime mover, which will increase the fuel in order to return the speed back to the original value, say 700, for example, RPM. Okay. So when you increase the load, the speed of the prime mover will be reduced. The governor will be responsible for this reduction in speed, and what it will do is increasing the fuel. Because of that, whenever you have more load, you have more consumption or fuel consumption. Okay, and this is coming from the opposition of the magnetic fields in the stator and in the rotor. So as a summary for the last section, when the load is increased, the voltage of the generator, it will be reduced, and also what? The speed, it will be reduced. Okay, the speed, it will be reduced because the magnetic field here will have more opposition with respect to the magnetic field coming from the rotor, so the prime mover speed, it will be reduced, and YE, it will be reduced because you will have more current taken from the generator, so more voltage drop will be in the coils of the stator, so the output voltage, it will be also reduced, as we explained before. So when you increase the load, the output voltage of the generator will be reduced, and the speed also, it will be reduced. The voltage reduction, it will be treated by the AVR by increasing the error signal going to the stator or exciter stator, then by increasing the finally the IDC, which will increase the flux. After that, E, it will return back to the required value. For the speed, the governor here will increase the fuel in the prime mover in order to return the speed back to the original value, so the frequency, it will not be affected. Now, if the load is reduced, the opposite will be happening. The voltage will be increased and the speed also will be increased. Okay, the AVR will reduce the error signal in order to reduce the IDC coming to the rotor. Okay, then the voltage will be returned back to its original value, and the prime mover governor here, it will decrease the fuel going to the diesel engine in order to reduce the speed to the set value or the original value. Again, we will concentrate on the frequency fault. If you have a reduced frequency in the generator, it means you have a mechanical problem in the prime mover. Check the fuel racks or the filters. Maybe you will find one fuel rack is stuck or something, and maybe one filter is closed. blocked. So this is for the reduced frequency of the generator. It is not an electrical fault, it is a mechanical fault related to the prime mover. If you have an over frequency, it means that you have a problem in the prime mover governor. Okay, so the governor here, it will be checked.